So this video is about mass and center of mass. And these topics are covered in Math 126, but they're usually covered very quickly. Sometimes like in the fall quarter, it's covered right before Thanksgiving or at a weird time. And then it is section 15.4 in the book, but I think usually like maybe there's one question on a midterm about it, maybe not, because the professor realizes there wasn't time. And then it's not learned very well. So hopefully we have time in this class to actually figure it out. These are just applications of double integrals. So one thing you might want to use them for is to find the mass. And if you have like something that's even thickness and mass all the way through, or density is the function that we use for it, then finding the mass of it is easy. You just multiply the density by the area. If you have something like a coin is actually pretty close, but not quite, right? Because there's texture to it. So it's a little bit denser in some places, but that's assuming it's uniform material. So, some places it's a little bit thicker. So you actually have a density function. If you pick a point on the coin, the density will change depending on where you are. So you could integrate that over this circle and you could find the mass of the coin. Then the next thing we would want to do is find the center of mass. And center of mass is the place where you could balance this on one finger, basically. The coin will be pretty close to the center because, as we said, the coin is pretty evenly distributed. Maybe something like this, where there's a heavy thing over here. I found this earlier. Let me see if I can find it again. So we can find the center of mass. Should be right around here. That's not terrible. Let's see if I can do better. There we go. Okay, so I can balance this. Center of mass is right around here. And the density function, it looks like it's pretty uniform here. This thing isn't very heavy. This thing might add some weight on this side, and then this thing definitely adds a lot of weight. So the center mass was around here, a lot closer to this side than to this side because of the mass here. So how do we calculate that? If you've done it with a bunch of discrete points before, you just take the weighted average. You multiply each point by its mass and add them together and divide by the number of points, and you get a center of mass. This is continuous, meaning there's points everywhere. But basically, you're doing the same thing. You're taking each point, multiplying by the density there, and then adding them together, or integrating. Integrate is just a fancy word for add. And then divide by the total mass, which you found via another integral. So that's what it is. There's some weird things in the formulas, that m sub x and m sub y, and I'll show you when we get to the writing down the formulas part. So there's a weird thing where the x coordinate of the center of mass is the m sub y divided by the mass. You might remember this from 126. Those are really badly named. M sub y is the moment about the y-axis. So like, let's look at this thing. Let's say like the origin is here in the center. Then let's say this is the x-axis and this is the y-axis. This thing has a tendency to fall this way if I just held it at the origin, right? So this is the y-axis. It has a tendency to fall this way, so it has a moment about the y-axis. If this were like a fulcrum about the y-axis, it would fall this way. And what that means is the x-coordinate of the center of mass is positive. So moment about the y-axis actually tells us where the center of mass is in the x direction. That's why the thing is flipped. M sub y in the integral, you see an x, and then it's flipped again. It goes to the x-coordinate of the center of mass, and same thing. So m sub x is the moment about the x-axis. It won't be very big in this case. As we said, this thing might be a little bit heavier, but it should be pretty close to the origin. But if I held it on the x-axis, it does have a slight tendency to tip this way, right? So moment about the x-axis is also positive. That just means the y-coordinate of the center of mass is positive. So hopefully some of those help clear up conceptually those issues, and then I'll just quickly go over formulas, and you already know how to calculate them. So as we said, all of this depends on some density function. This is the Greek letter rho, spelled this way, rho of xy. It tells you the density of the object over the whole area of the object. And then your mass, as we said, is just going to be the double integral over the object, call it region R of the density, dx dy, or convert to polar, or whatever you need to do. Okay, and then your moment about the y-axis, which really tells us whether or not it's going to tip over in the x direction, and if so, which way, is the double integral then over the region of x times your density, dx dy. That's really still taking a weighted average. We're taking every point multiplying by distance from the y-axis with density. And then that gives us the moment. And then the moment about the x-axis, which really tells us whether the y-coordinate of the center of mass is positive or negative and how big, is then this. We multiply by y, which is the distance from the x-axis. And you can switch the order of integration if you need to, as long as the functions are nice. Okay, and then, so finally, your center of mass, which I think your textbook denotes x bar comma y bar, is then, so x bar is my over m, and y bar is mx over m. But really, what we've done here, we could rewrite this. This is, if we were allowed to integrate like ordered pairs, that just means integrate each one. That's really just x comma y. Take every point, multiply by the density at that point. This isn't really good notation, but anyways. And then integrate that, divide by the mass. That's really what that is. So it's the same as if you had 5 different points. Like, let's say this was 5 pounds. There's a 5-pound point mass there. There's a 1-pound point mass there. There's a 100-pound point mass there. 10 pounds and 3 pounds. Then if somehow you had to hold all these up, you'd be holding, pretty close to the 100-pound point mass. That's probably the center of mass or close to it. And it's because you take a weighted average of all the coordinates weighted by the weights at each one. And that's exactly what this is.